Welcome! In this series of videos, we will cover the design and implementation of a project, from initial design through coding and development to testing, using the PowerBasic Windows and Console compilers. Today we will amend our application to create transactions between nodes. At the end of the last video, we had created an application which we can use to monitor our nodes in the blockchain demo. This monitoring application is created by the definition of a constant right at the beginning of the application. If that constant is defined, then our application will compile to an executable called blockchain demo monitor. If the constant is not defined, then our executable will be called blockchain demo. So now that we have created these two applications, our next task is to create standard transactions between the nodes, so that the nodes can actually initiate a transaction and can confirm a transaction has actually occurred. So what we will do is we will set up a set number of virtual assets on each node. Each of the nodes can then transact between 1 and 5 of these virtual assets to another node. And this will be the transactions that are happening between nodes during the run of the applications. To start this going, there's some preparatory work we'll need to do at the beginning of our application. We're going to set two new constants up, one called start asset count. This is the number of virtual assets that each node will have at the beginning of its program run, and the second constant is a node loop count. We're currently allowing the application to keep track of 500 nodes. This is specified in the max nodes constant. Our second constant is node loop count, which I'm initially setting to the value of 100. This will be the number of attempts to try and find a node to sell to. Our array of nodes is 500 in size, allowing the entire application to keep track of 500 separate computer nodes. And we're going to add a new global variable. This global variable is going to be called long assets, and this will be used to keep track for each node of how many assets it currently has. So when a node runs the application, we need to prepare the number of assets to be the same as the start asset count constant. So at the beginning of the application, each node will have exactly 100 virtual assets. So next we're going to do some work on the thread function, the monitor thread. I'm going to create two additional local variables to keep track of what the nodes are doing and how many assets are being passed between them. Next we're going to make some changes to one or two of the functions that already exist. There's a function called broadcast who I am. This function sends a message out to all the other nodes to let them know that this particular node is operational. And since each node will have a number of virtual assets, I want to pass another parameter to this function to say how many assets it currently has, so we can always see how many assets each of the nodes has at any point in time. So we will slot in this new parameter, which is the global of the number of assets. So we'll need to change this function so it can accept this new parameter. This function exists in our include file, and we can quite easily add in this as a parameter, str assets. So as this function has the purpose of sending out using UDP the name of the computer, that is this node, the phrase active, and we're adding on to the end of that a pipe delimiter and the number of assets we've passed in as the parameter. So as these broadcasts occur, we'll see how many assets each of the nodes actually still has. Next we want to look at the transactions. Up until now we have used a demo transaction mode just to simulate the sending of a transaction. So we're going to pad that one out a bit more now. Rather than saying demo transaction, we're actually going to put the transaction details in here. So we'll need to create a new function to build up a transaction. And this call to build up a transaction may or may not return a string. If it does not return a string, then this node at this current moment in time is not willing or able to send a transaction. So we can test the value of that string. And if the value of the string is an empty length string, then we know we have nothing to do. If it is not an empty line string, then we can call the existing raised_transaction function, passing the transaction details as the single parameter. So let's now look at the new function to build a transaction. So here is the skeleton of our new function to build a transaction. I'm going to set up two local variables here, one to contain the number of virtual assets to sell or transact to the other node, and another variable to keep track of the node we're talking to. Next, we have to determine if we actually have any of these assets to sell. So we'll need to test the global variable that holds the number of the assets. If this value is greater than 0, then we have some assets left. If the value is 0, then we have no assets left to transact. So how many assets should we actually attempt to transfer to the other node? As this is a demonstration program, we're going to use the random number generator to generate a value between 1 and 5. So each time we come into this routine, it will attempt to work out a number between 1 and 5 of the number of assets to transact. Now at this point, we haven't tested to see how many assets we actually have. So we need to ensure the assets that we wish to sell are not greater than what this node currently has. We can perform that using the min function, which will give us the minimum value between two separate variables. So the number of assets to sell is going to be the minimum of these two variables. Long assets is the total number of assets we have, and the number of assets to sell is the number that we've generated between 1 and 5. So if the number of assets we wish to sell is 5, and the number of assets we actually have is only 1, this will populate the assets to sell as 1. This way you can never sell more assets than you actually have. So having determined how many virtual assets we are going to sell, we now have to decide which node to sell them to. So we're going to create another new function. This function is to pick an active node. As I said earlier, we have the potential of 500 nodes in the entire network. In today's run, we're only going to have 4 active nodes. So we have to identify which of the nodes are actually active and which we can actually sell to. If the value returned from this function is an empty line string, then there are no nodes available and we can exit this function. If we do get a value coming back from this function, then that's the node we're going to be selling to. So in that case, the return of the function is the name of the node, a pipe delimited character, and in a string, the number of assets to sell. So having completed this function, we now have to create our new pick an active node function. So the purpose of this function is to sweep through the nodes array and work out which of the nodes are actually active and which we can actually send to. So I'm going to create 3 local variables. One for a loop count, one for a node, and one for this computer as a string. The nodes array will have a list of all the nodes that are active at the moment. The one thing you don't want to do is to attempt to sell to your own node. So we're going to sweep through the nodes array using loop count in a for next loop. So within this for next loop, we're going to pick up a random number between 1 and the maximum number of nodes, which is currently 500. As we're only going to be using 4 nodes in the network today, most of the time this will return a number for a node that is not active. This will ideally slow down the generation of transactions, which will help as we want to actually monitor them by eye. Computers can do things very, very quickly. Mere mortals like you and me need a little more time to see what's happening on screen, so this will effectively slow down the system enough for us to see what's happening. So having determined a node we wish to transact with, we first have to test to see is this or is this not an active node. So we will test the condition of the node to see whether it is active or not. If it is not active, then we will go to the next iteration of our for next loop. So each time this function is called, we will be testing between 1 and the node loop count. That's between 1 and 100. We will have 100 attempts at picking a computer to transact with. So having found a node that is currently active, we need to ensure that it is not the node that is actually running at the moment. So we can test that against the computer name. So if the work name is the same as this computer's name, then we will iterate the for next loop. Otherwise, we can actually return the name of the node. And at that point, we can exit the function. If we get to the end of the for next loop, then we're returning an empty len string, as we have been unable to find a node to transact with. So now that we have built up a transaction and selected a node to transact with, we can now move on to handling the messages coming back from other nodes. In this function is a section that determines what we do with incoming messages. At the moment we have the phrase active or not active. We do not have anything that handles a transaction. This is a transaction coming into the node. So we'll need to create a case statement to handle these transactions. And as we have done before, we're testing the definition of the monitor constant and only handle these if we're not actually doing any monitoring. So if a transaction message does come in, it may not be for this node. So we next have to test to see, is the transaction for this node or not? So we're parsing the message that comes in. The third element of the parse is the name of the computer that this transaction is aimed towards. So if it does not match the name of this node, then we can ignore it. Next, we have to pick up the number of assets that the sender is actually sending. This is the fourth parameter in the message. Again, using the parse command and converting it to a number and storing it in the long assets received. So if we've got this far, then one of the other nodes wishes to send you, this node, X number of assets. At that point, we can then add that to our assets. So if we started off with 100 assets, and one of the other nodes wishes to send us 2, we would now have 102 assets. In order for the other node to reduce its asset count by the amount it sent us, we now have to send a message back to confirm the transaction to the sender. So to acknowledge the transfer back to the node that sent it, we need to populate the transaction string. The transaction string has 2 elements: the node you wish to transact to and the amount that you're transacting. So as we've received in the number of assets from the sender, we're now sending this back to confirm that we have actually received. And we're going to create another new function whose job it is to confirm the transaction. And this new function is going to be remarkably similar to the other raise transactions we've already done. So we will create that in our encode file. And here is our new function. It takes in a string which is the transaction details, which contains the node and the amount, and we're using the UDP send command to send that transaction. The phrase we're using this time is confirm. So we're sending the confirmation back to the node who sent us it in the first place. So as you can guess, we need to put another case statement in our monitoring thread function. This is to handle confirm messages. This is looking for the phrase confirm, and we will only action this if we're not running as the monitoring application. As we did before, we need to check to make sure that our node is the node that this confirmation is actually for, as each node will receive these messages. So we're testing the third element of the message to see if it's our computer. If it is, then we know we can pick up the number of assets and we can reduce our total asset count by that number. So we're picking up the number of assets by the message coming back in the fourth element of the message. And we're subtracting that from the total number of assets we currently have. So we have embellished the transaction handling and we have added more handling for confirmations. So when the application actually runs on a node, it will first attempt to communicate with the other nodes to say that this node is currently active. Then, having done that, it will attempt to find another node which is currently active, which it can actually transact to. It will work out the number of virtual assets to send, and then it will communicate with that node. It will then await for confirmation coming back from that node, and once the confirmation comes back, it will reduce the number of virtual assets it has by that number. So now that we should have everything in place, all we need to do is to actually test it. So first, we will compile the application. We have to do two compilations here. The first is going to be to compile the monitoring application, which has created a blockchain demo monitor application. Next, we will comment out the monitor, and we will compile again. This will create our blockchain demo application. We now have to copy this blockchain demo application to the 4 computers we're going to be using. And that's all 4 computers with updated executables. We will now run our blockchain monitoring application on the computer we're currently on. And it's now listening, waiting for other nodes to become active. So we will remote connect onto each of the other nodes and activate them. That's our first node, and our second, and our third is now active, and the 4th node is running too. So we can see we've had activations from all 4 computers, and they're each saying at the moment that they have 100 virtual assets in the bank. We now have to wait for the nodes to start transacting. As there are only 4 nodes going at the moment, it will take some time for this to happen, so we'll just advance forward in the video until they start transacting. And there are our first transactions happening. We have Odroid number 1 starting a transaction with Odroid number 2 for 4 assets. And there is Odroid number 2 confirming its transaction with Odroid number 1 for 4 assets. And we have a second transaction between Odroid 2 and back to Odroid number 1 for 3 assets. And there is the confirmation. So what we should see the next time we get an active message is the numbers will start to change. There is Odroid 1 showing that it now has only 99 virtual assets left, and Odroid number 2 has come out slightly better and it now has 101. And the transactions are starting to come in thick and fast now. Here we have Odroid 1 transacting with Odroid 3 for 5 assets. On Odroid's 1 asset count is now dropping down. So what we've achieved today is we have set up transactions between nodes. Each node has a certain number of virtual assets at the beginning. It will then randomly choose another node which is currently active to transact with. So now that we have all this infrastructure in place, what we'll be doing in the next video is actually recording the audit history by using blockchain. Hopefully you found this demo interesting. But that's it for today. Thank you for watching.